Alright, this is part 2 of my video on graphs versus level sets. This is problem 2b from the week 5 problem set, and it sounded like you all came to some correct answers on this one after working through this and struggling with it for a bit. I want to talk about a way of doing this that saves you a little bit of trouble, because I know that some of you asked, how in the world do you take partial derivatives of this? And the answer is, well, you can take partial derivatives of this very carefully. But I put this complicated expression on the problem set in order to encourage you to be savvy about how you attack this problem. Right now, what we're looking at is a level surface of a really complicated function, natural log of x squared y plus 2yz over z. That's a function of 3 variables, which means that the level set will be a level surface, and it's the function equal to 0 level surface. Now, I could go ahead happily along and take partial derivatives of this with respect to x, y, and z, get a normal vector, get a tangent plane. But I'm not going to do that because I don't feel like taking complicated partial derivatives this evening. I'm going to try something else. This is a statement about a natural log being 0, which means I can use algebra to think about this statement differently. After all, if the natural log of this expression is equal to 0, then that means that this expression has to be 1, because 1 is the only number whose natural log is equal to 0. So I know that x squared y plus 2yz over z equals 0. Another way of thinking of that, not 0, 1. Another way of thinking about that step, by the way, is you can raise e to both sides. So e to the natural log of all this stuff, and the e and the natural log cancel out, equals e to the 0, which is 1. So another way of thinking of the same thing. So now I have this statement. But you know what? Taking partial derivatives of this seems only a little bit better, not a lot better. I'm still not crazy about the idea. So I'm going to do something else. I'm going to multiply both sides by z and get x squared y plus 2yz equals z. Now there's a problem here. I'm no longer thinking about a level set of a particular function. If I think of this as my function on the left side, I'm talking about when that's equal to z. That's not a level set because I'm not setting the function equal to a constant. So I need to move everything that is not constant to one side of the equation so that one side of my equation will be a constant. So I'm going to move z over, get x squared y plus 2yz minus z equals 0. And now I have a function of 3 variables, x squared y plus 2yz minus z, which I'm setting equal to 0. So I have a g equals 0 level set, or level surface, where g is equal to x squared y plus 2yz minus z. All right, I'm going to go ahead and record that someplace else so that I have it and can work with it. G equals x squared y plus 2yz minus z. I'm going to get rid of everything else so that it's not cluttered. Oh, wait, I still need my point, though. Let's check that. It was 2, 1, negative 4. Yes. Okay. Now, the thing to keep in mind is I've changed the function, or at least it seems like I've changed the function I'm working with a lot, and I have. I've gotten rid of the natural log, and I've gotten rid of the fraction in that formula for the function. But what's cool about this is I'm still talking about the same surface, because after all, the statement that this is equal to 0, is algebraically equivalent to the statement that the natural log of that ugly fraction is equal to 0. I got there by algebra. Now, there are places where that's not exactly true, where the two are not equivalent, like places where the natural log might be undefined, for example, but I know I'm not dealing with one of those. At least I don't think that I am. Anyway, you can check that for yourself. But now, let's use calculus to find the normal vector to this level surface at the point 2, 1, negative 4. Now that I'm talking about a level surface, I can go ahead and take the gradient and expect that to be the normal vector. The gradient of g at xyz is going to be equal to 2xy I plus x squared plus 2z j, that's my y partial, and my z partial is going to be 2y minus 1, so I'm going to have a k there. I'm interested in the point 2, 1, negative 4, so my gradient vector there is going to be, let's see, 2 times x times y, that's 4i, x squared plus 2z, that's going to be, let's see, 4 minus 8, that's minus 4j, and then 2y minus 1k, that's going to be just a plus k. I already have my normal vector. My normal vector is going to be 4i minus 4j plus k. You'll notice I didn't have to do anything with this point except for putting it into this formula to find the gradient at that specific point. Alright, now what's my tangent plane? To find the equation of the tangent plane, I'm going to use these components and set up my equation for a plane from this point normal to this vector. My vector is 4i minus 4j plus k, so I have 4x minus 2 minus 4y minus 1 plus 1 times z plus 4. All that should equal 0. Again, not because that has anything to do with the value of g, but because this is a statement about two vectors being perpendicular, which means that their dot product is always going to be 0. So there's my tangent plane equation. That's a clever way of handling that problem that doesn't require as much ugly partial differentiation as what you might have done if you hadn't thought about rewriting the equation. Okay, so in summary, if you want to find normal vectors to a graph, try thinking of the graph as a level surface of a function of 3 variables somehow. That means you got to introduce a z-coordinate as the value of a function of 2 variables, and then rearrange the equation so that you're dealing with a function of x, y, and z, and you have that whole thing equal to a constant. The way that we usually do that is by subtracting some terms over to the other side so that we have one big glob in terms of x, y, and z equal to 0 or equal to some other constant. Anyway, that's the end of the video. I hope this was a little bit helpful or illuminating. If you still have questions, feel free to email me or post them on this YouTube video. I'll be glad to try and answer them the best that I can. Have a great weekend, and I hope you do great on your tests.